let us start with topic 2 of this course, that is traditional methods of optimization. Now, the traditional optimization methods are also known as the conventional optimization methods. Now, these methods can be broadly classified into 3 groups. One is called the linear programming method, next is nonlinear programming method, and we have got the specialized algorithm. Now, this nonlinear programming method, it could be either graphical method or simplex method. Now, supposing that I have got a problem having only 2 variables. Now, for this problem I can go for the graphical method of linear programming, but supposing that I have got more than 2 variables. So, there is no way out, but we will have to go for the simplex method. Now, then comes the specialized algorithms. Now, these algorithms are required to solve some special problems, and these algorithms are known as integer programming, geometric programming, dynamic programming, and so on. And now, if I concentrate on the nonlinear programming methods, those are further classified into 2 subgroups. Now, one is called the single variable problem, another is called the multivariable problems. Now, single variable problems can be solved either by using analytical method or some numerical methods. Now, analytical method I have already discussed, that is the method of calculus. That means, we will have to find out the derivative of the function with respect to the variable, and we will have to put equals to 0, and we will have to solve and find out the optimal solution, which I have already discussed. Now, I am just going to concentrate little bit on the numerical methods. Now, these numerical methods includes exhaustive search method, dichotomous search, Fibonacci search, golden section method, and so on. Now, similarly, if I see the multivariable problems, now these multivariable problems can be further classified into 2 subgroups. One is called the direct search methods, one is called the direct search method, another is called the gradient based method. Now, in direct search method, we use the value of the objective function to help that particular optimization tool, whereas in case of gradient based method, we take the help of gradient direction to find out the search direction of this particular optimization tool. Now, we have got a few direct search methods, for example, random search method, pattern search method, and so on. Similarly, we have got a few gradient based methods like steepest descent methods and others. Now, out of all the traditional tools for optimization, this steepest descent method is found to be the most popular one. Now, here in this particular course, I will try to explain the working principle of a few optimization tool, and let me start with one numerical method which is popularly known as the exhaustive search method. Now, let us consider an optimization problem of the form maximize y equals to f x. So, this is the function which I will have to maximize, and let me assume that. So, this is a unimodal function. So, maximize y equals to f x. subject to x is lying between x minimum and x maximum, and let me consider one unconstrained optimization problem, and this is actually the plot of the objective function. So, y is a function of x, and as I told, I am considering one unimodal function like this. Now, how to proceed with this particular algorithm to find out the optimal solution? To find out the optimal solution, actually what I will have to do is, so I will have to find out the range for x, that is nothing but x maximum minus x minimum. Now, this range is divided into some equal parts, and let me consider small n equal parts. Then the small x change in x, that is delta x, is nothing but x maximum minus x minimum divided by n. Now, step 1, we set x 1 equals to x minimum, x 2 equals to x 1 plus delta x, that is nothing but x I 1, that is the first intermediate, x 3 equals to x 2 plus delta x, that is x I 2. Then we go for step 2, where we try to calculate the values of the function like f x 1, f x 2, f x 3, and we try to compare. Now, if f x 1, if f x 1 is found to be less than equals to f x 2 and it is found to be greater than equals to f x 3, then we say that the maximum point lying in the range of x 1 comma x 3, and we terminate the program. Else we assign x 1 equals to x 2 previous, x 2 equals to x 3 previous, and x 3 equals to x 2 present plus delta x. Then we go for step 3, we check whether x 3 exceeds x maximum. If x 3 does not exceed x maximum, we go to step 2. Else we say that the maximum does not lie in the range of x 1 minimum comma x 1 maximum. Now, I am just going to solve one numerical example just to explain the working principle of this particular the method. So, let me take the numerical example like this: maximize y equals to f x, that is 2 x square minus x cube. Now, so this is actually the objective function which I will have to maximize, subject to x is lying between 0 and 2. Now, this is nothing but the function plot. This is a function of only one variable. So, y is a function of x. So, this is actually the plot of this particular the function, and I will have to find out the maximum value of this particular the function. Now, here x minimum equals to 0 and x maximum equals to 2.0, and let me consider small n is equal to 10. Now, the change in x, that is delta x, is nothing but x maximum minus x minimum divided by 10 is equals to 0.2. So, we set x 1 equals to x minimum, that is equals to 0.0, x 2 equals to x 1 plus delta x, that is equals to 0.2, x 3 equals to x 2 plus delta x, and it is equals to 0.4. Now, we determine the function values. F of x 1 is found to be equal to 0.0, f of x 2 is found to be equal to 0.072, and f of x 3 is coming to be equal to 0.256. Now, here f x 2 is found to be greater than f x 1 and it is found to be less than f x 3, and we conclude that the maximum does not lie in the range of 0, 0.4. Next, we set x 1 equals to x 2 previous, that is equals to 0.2, x 2 equals to x 3 previous, that is equals to 0.4, and x 3 equals to x 2 present plus delta x, that is equals to 0.6. And once again we calculate the function values and try to check whether that particular condition is fulfilled or not. Now, for this particular function, analytically we can find out the optimal value. Now, this function is actually the mathematical form of this particular function is nothing but 2 x square minus x cube. So, 2 x square minus x cube. So, if I try to find out the analytical solution, we can find out easily. So, y is nothing but 2 x square minus x cube. So, what we do is we try to find out the derivative, that is dy dx, and that is nothing but 4 x minus 3 x square, and we put this equals to 0 and we solve for x. So, this is nothing but x 4 minus 3 x, that is equals to 0. So, either x equals to 0 or 4 minus 3 x equals to 0. So, x cannot be equal to 0. So, we can find out x is nothing but 4 by 3, that is your 1.333. So, we can find out the maximum value of this particular function is coming at x equals to 1.333, and the maximum value of this particular function is coming as 1.185. So, analytically you can find out the solution, and I can also check through this exhaustive search method, and I can find out, I can indicate one range for this particular value of x, where I will be getting that maximum value of this particular the function. Now, if I take a higher value of small n, there is a possibility I will be getting a closer range of the value of the x, where I will be getting that particular the maximum value of this particular the function. Now, here I just want to mention that this particular method will be applicable only for the unimodal function. For the multimodal function, so this tool may give rise to some problem to determine the maximum or the minimum value of this particular function. Now, I am just going for another tool that is known as the random walk method. Now, this random walk method is nothing but a direct search method. Here the search is carried out using the information of the objective function value. That means, we consider the numerical value of the objective function to determine what should be the search in the next iteration. And in this particular method, we do not use the derivative or the gradient information of the objective function. Now, according to this particular method, the rule for updating is nothing but this, that is your x I plus 1 is nothing but x I plus lambda u I. So, capital X is actually a collection of all the design variables like small x 1, x 2 up to say x m, if there are m such design variables. So, capital X I is nothing but the value of this particular the set of the design variables in earlier iteration, and lambda is nothing but the step length and ui indicates the search direction. Now, how to find out? So, this particular search direction, so that I am going to discuss. Now, as I told that capital X is nothing but a collection of all small x values and lambda is nothing but the step length. Now, here we try to find out the search direction, that is ui, that is nothing but 1 divided by square root of r 1 square plus r 2 square plus dot 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 plus r n square multiplied by r 1 r 2 r n transpose. So, this will give you that search direction. Now, once I have got the step length and the search direction, so very easily I can find out what should be the values of the design variables in the next iteration. Now, here in this particular expression, this r 1, r 2, r n are nothing but the random numbers lying between -1 and +1, and here we consider the number of random number, that is small n, that is equal to the number of variables, that is small m. Now, let us see this particular algorithm in the form of the steps. Now, supposing that I am solving one minimization problem, and let me concentrate on the step 1. So, we set initial values of lambda, that is the step length, and epsilon, that is the permissible minimum value of lambda, and capital N indicates the maximum number of iterations to be tried. We start with an initial solution x 1 created at random, and we try to determine the value of the objective function, that is f 1, that is nothing but f of x 1. Now, then we go for step 2. We generate a set of n random numbers lying between -1 and +1, and we try to calculate what should be the search direction, that is u 1. Now, step 3, we determine the function value, that is f 2, that is nothing but f of x 2, f of x 2, that is your f of x 1 plus lambda u 1. So, lambda is the step length, u 1 is the search direction, x 1 is the previous value. So, I can find out x 2. Once I have got x 2, I can find out the value of the objective function. Then comes step 4. Now, as I told that this is a minimization problem. So, if f 2 is found to be less than f 1, then it is a good solution. Then we set x 1 equals to x 1 plus lambda u 1, and we set f 1 equals to f 2, and we repeat the steps 2 through 4, else repeat steps 2 through 4 up to the maximum number of iteration, that is capital N. So, step 5, if a better point x I plus 1 is not obtained after running the algorithm for n iteration, we reduce lambda to 50%, and once again we try to repeat those iterations. Now, step 6 is the modified lambda. Now, as I told, we reduce lambda to 50%, and for a particular value of lambda, we run this algorithm for capital N iterations. Now, we go for the reduction of the lambda through a number of iterations, then we reach the minimum permissible value for this particular lambda, which is nothing but epsilon. So, we go for step 6 for checking is the modified lambda is less than epsilon. Now, if no, we go to step 2, else we declare that x star is equals to x 1 and f star is equals to f 1, and we terminate the program. Now, this particular algorithm is very popular, and I am just going to explain the working principle of this particular algorithm with the help of one numerical example. Now, here I am just going to minimize one function, that is f of x 1 x 2 is nothing but 4 x 1 square plus 3 x 2 square minus 6 x 1 x 2 minus 4 x 1, subject to x 1 x 2 is lying between minus 10 and plus 10, and here I am not considering any functional constraint. So, this is unconstrained optimization problem. Now, if you see the function plot, so I can find out this function plot. Now, this is a function of two variables x 1 and x 2. So, I will be getting this particular the plot for the function, and our aim is to find out the minimum solution, the minimum point. And here we take lambda, that is the step length, equals to 1.2, epsilon, that is the minimum permissible value for lambda, and this is it is equal to 0.075, and n is the number of iteration, and that is equals to 100. Now, we just go for iteration 1. We take the random initial solution denoted by capital X 1, and that is nothing but 0 0. Next, we try to find out the function value, that is f 1, that is f of x 1, and that is 0.0. Take two random number lying between minus 1 and plus 1, supposing that r 1 equals to minus 0.5 and r 2 equals to 0.2, and using the value of these particular random numbers, now I can find out the unit random vector which is going to indicate the search direction. So, u 1 is nothing but 1 divided by square root of r 1 square plus r 2 square multiplied by r 1 r 2, and if I calculate, so I will be getting the numerical values like this. I will be getting the numerical values like this. The next is, so x 2 is nothing but x 1 plus lambda u 1, then function value f 2 is f of x 2, and that is nothing but f of x 1 plus lambda u 1. Now, if I substitute the value of x 1, that is nothing but 0 0, and lambda I have already calculated, sorry, I have already taken as a fixed value, and u 1 is the search direction I have already calculated. Now, I will be getting that is nothing but f of minus 1.1142 comma 0.4457, and I will be getting this particular value of the objective function. Now, as f 2 is found to be greater than f 1, f 2 was 0.0. So, f 2 is found to be greater than f 1. So, this particular solution cannot be considered as x 2, because this is not a good solution. So, we go for the next iteration. Now, this particular process will go on and go on, and once it reaches that particular value of capital N, we reduce the value of lambda, and for the reduced value of lambda, once again we run this particular algorithm for capital N number of iterations, and we try to find out whether we can get that optimal solution or not. Now, I am just going to discuss another very popular traditional tool for optimization, which is very popularly known as the steepest descent method. Now, its name indicates that this is a gradient based method, and we try to search in a direction opposite to the gradient, and on principle this can solve the minimization problem. And let us see how does it work. And before I go for the working principle of this particular method, let me mention that this method is not suitable for discontinuous objective function, because the gradient does not exist for that discontinuous objective function. Now, to discuss this algorithm, so what I will have to do is I will have to first define what do you mean by the gradient of a function. Now, supposing that I am considering y is a function of capital X, and that is nothing but capital X is a collection of m number of small x values. So, this is a function of m variables. Now, its gradient is defined as delta f is nothing but partial derivative of f with respect to x 1, partial derivative of f with respect to x 2, comma, and the last term the partial derivative of f with respect to m transpose. So, this is nothing but the gradient of this particular the function, and gradient direction is nothing but the direction of steepest ascent, and that is why. So, we will have to move in a direction opposite to the gradient, and it names indicates this is a steepest descent method, and on principle it can solve the minimization problem. Now, the principle of this particular method, we start with an initial solution x 1 and we move along the search direction according to the rule x I plus 1 is nothing but x I plus lambda I multiplied by S I. So, S I indicates the search direction, and that is nothing but minus delta f I, that is opposite to the gradient, and lambda I is nothing but the step length, and this is the rule for updating. Now, let me take a very simple example. Supposing that I have got a function, objective function of two variables x 1 and x 2. Now, depending on the value of the y, so y is a function of two variables x 1 and x 2. So, for a particular value of y, I can find out the contour plot, another value of y, another contour plot, another contour plot, another contour plot I will be getting. Now, this particular algorithm starts with an initial solution selected at random. Supposing that at the beginning the algorithm is here only. Now, it will try to find out the search direction for the next iteration, and it will try to move along the gradient direction. Once again it will try to follow the gradient direction, and gradually it is going to reach that particular the minimum solution. This is the way actually this particular algorithm, starting from an initial random initial solution, will try to move towards the globally optimal solution. Now, I am just going to take one numerical example to solve this particular to show the working principle of this particular algorithm, but before that let me mention the termination criteria of this particular algorithm. Now, the termination criteria are as follows: the rate of change of the objective function value, that is nothing but the mod value of f of x I plus 1 minus f of x I divided by f of x I. So, this particular mod value should be less than equals to some small value epsilon 1, or what I can do is I can find out the partial derivative with respect to the variables, and their mod values should be less than equals to epsilon 2. So, this could be the termination criteria for this particular the algorithm.